It's my pleasure to give a talk on superradiant bosons driving supermassive black hole mergers. This is based on our recent work in collaboration with Minxi和 Vladimir Takhistov, Hui Yuzhu. In our universe, there are a lot of mystery. One of them is what is dark energy, what is dark matter. Interestingly, the lightest object in our universe, ultralight boson, can be candidate for them. Ultralight boson with mass around 10 to minus 33 electron volt can be candidate for the dark energy. Mass from 10 to minus 32 to 10 to minus 27 electron volt can be candidate for the early dark energy to solve hypertension. Mass from 10 to minus 22 to 10 to minus 21 electron volt can be candidate for the fuzzy dark matter to solve small scale problem for cold dark matter. And for higher mass range, ultralight boson can be the candidate for the QCD-XL. Also in our universe, the heaviest object is supermassive black hole. We already take a photo by the Event Horizon Telescope from the galaxy M87. So the interesting thing is, what if the lightest object, ultralight boson, meets the heaviest object, supermassive black hole? What happened? In such a case, superradiance instability happens. What's that? For rotating core black hole, there is a negative energy Gauss surface around them, and when an incoming boson wave with a positive energy in this ergo surface and will be ejected outside, become an outcoming wave with a higher energy, larger than their incoming energy. This is so-called Penrose process. Since this outcoming wave, the boson is a massive particle, so they are gravitational bonded and return becoming an incoming wave and keeping this Penrose process. Since such a this is a Penrose process is it will keep extracting energy from the core black hole and lower down the spin of the core black hole. Therefore, such a loop Penrose process will stop until the core black hole angular velocity is smaller than the critical value. And this kind of process will accumulate a very massive dense boson cloud around this core black hole. So let's first describe the physics about this boson cloud. So we first apply the Klein-Gordon equation in the background curve spacetime matrix, and in here there is a gravitational fine constant alpha to describe it. When this alpha is very small, around order 0.1, this Klein-Gordon equation can be simplified to a gravitational shielding equation, and we can solve them while this three parameter NLM. And this will tell us the profile of this boson cloud. And since we use a gravitational shielding-like equation to solve it, we also call this boson cloud with this black hole as a gravitational atom system. And to describe them, we first describe their size, like we use a Bohr radius, which depends on the boson mass and alpha. For example, for black hole with mass 10 to 10 solar mass, boson mass 10 to minus 21 electron volt, the Bohr radius is around 0.1 parsec. And also, this boson cloud, this gravitational atom, was formed while the Penrose process, this superradiance instability. There must be a time scale. We calculating, for example, 10 to 10 solar mass alpha equal 0.1. The formation time scale is around 10% of the age of universe. So as we call them as the gravitational atom, like atom, they must have an energy spectrum. The gravitational energy spectrum, their energy depends on this three parameter N, L, and M. Here we label different energy for the gravitational atom. And since we have energy spectrum, so there must be some state transition from one state to another state. Since this gravitational atom is gravitationally formed, so this transition should be gravitationally perturbed. And therefore, when this gravitational atom has a binary companion around them, they will introduce a perturbation, gravitational perturbation. This perturbation will cause a transition from one bounded state to another bounded state when a binary companion orbital frequency match the energy difference between two states. For example, for 10 to 10 solar mass black hole, alpha around 0.1, this orbital frequency for binary companion should be around the nanohertz band. And once we know the bound state transition, we also want to know what's the transition rate from one state to another state. Therefore, we need to first introduce two kinds of transition. One transition is floating orbit transition. This will make the binary companion stay in such a transition for very long time, since the angular momentum of the binary companion increase during such a transition. Another one is sinking orbit transition. That is, the binary companion will faster pass such a transition. The transition timescale is very short since the angular momentum during such a transition is decreased. Therefore, we can calculating their transition rate while how gravitational perturbation transfer from one state to another state and how such a transition angular velocity change rate changes. Apart from the bound state transition via this resonance, another one is ionization. This ionization is to transfer a bounded state to an unbounded state. That is, when a binary companion, their angular velocity corresponding with the energy scale, which is larger than the ionized energy for this bounded state. Such an ionization will happen. In principle, ionization is keep transfer a bounded state to an unbounded state. That is, keep extracting energy from this orbital binary to outside. Therefore, this is a dispersion channel, energy channel. Therefore, the energy is keep decreasing. So this behaves is like a dynamical friction. Therefore, actually, the ionization in gravitational atom system is a dynamical friction. To describe them, we can use a classical channel called dynamical friction power to describe the ionization in gravitational atom. Now we already studied the background physics for gravitational atom superradiance around the supermassive black hole, but we need a physical laboratory to test it. In our universe, we rarely observe a physical supermassive black hole, which can be a physical laboratory for us. This supermassive black hole system is called OJ287 system with primary black hole mass 10 to 10 solar mass and the secondary black hole mass 10 to 8 solar mass. Their orbit period is around 12 years with a orbital decay rate. And we calculating their orbital decay power using the observed value. We hope this orbital decay power can be explained by the gravitational wave emission. However, after we calculation, we find these two values do not match with each other and with a 4.3 sigma inconsistency. So that means there must exist an additional energy dispersion channel around OJ287, which can help us to understand this orbital decay power. So what if there is a boson cloud exists around OJ287 system combined with and their dynamical friction will combine with the gravitational wave to explain the orbital decay rate in OJ287? So in order to understand that, the first things that we need to know is what's the cloud state in OJ287 system. As we said, the fastest growth state in boson cloud is 211 state. So we first check the formation timescale for 211 state. We find it's around 0.3% of the age of universe. So therefore, this 211 state can form in our in current OJ287 system. Meanwhile, we studied the orbital frequency for OJ287 is around 3.5 nanohertz, which is larger than the transition frequency from 211 to 311-1 frequency. That means such a transition from 211 to 311-1 already happened. Therefore, we need to calculate the transition rate between 211 and 311-1. And we're calculating and we find that for OJ287 labeled by this red star, actually more than 99.5% boson cloud will remain in 211 state. Only very, very little will be transferred to 311-1. Therefore, in order to calculating the boson cloud around OJ287, we just use 211 state. That's fine. Also, once we know their state, we need to know what's their density profile around the OJ27. We need to calculating them using the from the gravitational shielding equation. We find this wave function, and we using this wave function to calculating the density profile. You can find this right curve is for 211 state. Their distribution is up to the one order 1 parsec. So now let's calculating the dynamical friction power from 2-ion state or in OJ27. We apply this dynamic 2-ion state density distribution in dynamical friction and calculating it. And we find that for different boson mass, they will give a different dynamical friction power. And in order to explain the additional dispersion energy in OJ27 system here, this require the boson mass is from 8.8 to 9.3 times 10 to minus 22 electron volt. This kind of boson mass from the boson cloud induced dynamical friction can explain the observed tension in OJ27. However, such an observation is not very certain. Therefore, in future, more precise measurement, if we find actually there such a tension do not exist, that means the dynamical friction power contributed from superradiant boson cloud is very weak, and their contribution to the total gravitational wave power is maybe smaller than 1%. That means we can rule out some parameter range, like if the boson mass in this match range, like here, the, their dynamical friction already larger than this 1% or 1% contribution. Therefore, if in the future observation we didn't find such a tension exist, that means the boson mass should not in this mass range. We put a very strong boson mass bond on it. And such a mass bond is independent on any dark matter assumption. We do not require such a ultralight boson play a role in the dark matter. So this is interesting. So apart from the OJ27, this kind of very interesting physical laboratory, is there some other imprint that superradiant boson cloud will leave in our universe, in our observation? For example, currently we already observed the stochastic gravitational wave from the nanogram, the PTA observation. And this indicates that the supermassive black hole will merge. But this will cause a problem, that is final-parsec problem. That is when two galaxies merge and their center supermassive black hole will merge, and the supermassive black hole will shrink their orbital while eject the surrounding star and gas. However, when the separation between the supermassive black hole is around 1 parsec, there is no surrounding star and gas for them to eject to help them shrinkage their orbit. Therefore, the supermassive black hole will keep this separation, 1 parsec separation, more than the age of universe. So if some mechanism can help them to overcome this final parsec to this 0.01 parsec, then the gravitational wave emission will dominate it and help them merge. So the key point is we need to find, in order to solve final parsec problem, we need to find a mechanism to help the supermassive black hole to overcome this final parsec. In such a case, the superradiant boson cloud can help them. Their dynamical friction can speed up their shrinkage. As we said, we need to first study the cloud state around the supermassive black hole. Anyways, the fourth state is 2-ion state, and during their final parsec, this will trigger a transition from 2-ion to 3-ion minus 1. And here we can find more than 90% 2-ion state will be transferred to 3-ion minus 1. And also the next transition will happen from 3-ion minus 1 to 6 to minus 2 state. Here we can find in such a transition, more than 99.8% will remain in 3-ion minus 1. That means around the supermassive black hole in final parsec, the major cloud around supermassive black hole boundary is 2-ion state and 3-ion minus 1 state. So we just considering the 211 state density profile and the 311 minus 1 state density profile with different ratio contribution to the total boson cloud density distribution, and apply it in the dynamical coefficient calculation, apply in the supermassive black hole boundary major axis shrinkage. And in order to solve the final-parsec problem, we require the semi-major axis evolution from order 1 parsec to 0.01 parsec. Their evolution timescale must be smaller than 1 gigayear. We see this can solve the final-parsec problem. Therefore, here we plot some parameter range where they should have final-parsec problem, but their final-parsec problem can be solved by the existence of superradiant boson cloud around them. And here, for example, we find for a boson mass around 10 to the minus 21 electron volt, they can solve final-parsec problem for 10 to order 10 to 9 solar mass to 10 to 10 solar mass. They can partially solve the final-parsec problem. And also, when the superradiant boson cloud exists around supermassive black hole, they not only help us to partially solve final-parsec problem, but also they will leave imprint on stochastic gravitational wave background. Here, when we're calculating their energy emission per frequency, the existence of the dynamical coefficient from superradiant boson cloud will decrease the characteristic string of stochastic gravitational wave background. And you can find here for pure gravitational waves emission in nanograv data, they are black line. And when we introduce the existence of the stochastic existence of boson cloud, they will express the nanograv data characteristic string. And also there is a turnover feature happen in some specific frequency, which can help us to distinguish from the other scenario. Therefore, the existence of superradiant boson cloud in OJ27 system, they can reconcile the potential tension with the boson mass 10 to 8.8 to 9.3 times 10 to minus 22 electron volt. And also, if such a tension do not exist, we can put a very strong bond on the boson mass here. This is independent on the dark matter assumption. Meanwhile, the superradiant boson cloud around supermassive black hole, they can partially solve the final-parsec problem and leave some unique imprint on the stochastic gravitational wave background. That's all. Thank you.